Now let's first start with how the perception of the pain plays an important role in sickle cell disease. When sickle cell disease patients seek emergency room care for pain management, opioids are generally prescribed. However, this practice comes with a critical downside because over time, some patients might request opioids even when they're not clinically necessary. This leads to a dangerous cycle of addiction, dependency, and so forth. And this is further complicated by this societal perceptions. For example, there's a misconceived stereotype that certain racial groups are more likely to misuse drugs, which can lead to both overtreatment and undertreatment. Now, specifically, individuals genuinely in need of the pain relief might face skepticism or denial of treatment due to these prejudices making things worse, making people suffering. And this creates a dilemma of medical and societal injustice. Also, pain is considered the hallmark of sickle cell disease, meaning that it will be the most representative marker of severity. It could be a severity of sickle cell disease, and it can also play a key role in understanding the mechanisms of the disease itself. For example, vaso-occlusive crisis or the frequency of that crisis may be related to how sensitive you are to pain. When we usually feel the pain, we would get vasoconstriction in the body or blood network, but then narrowing the vessel can trigger a vaso-occlusive crisis in sickle cell disease. And we can also imagine the next crisis as a chain action, because that vaso-occlusive crisis would cause pain, and that pain would trigger another vaso-occlusive crisis event. So because of these reasons, it is so helpful to understand how much you would respond to pain in an objective metric. And this leads to our first hypothesis of the study. So here is our study setup finally. Hypothesis would be if you have a severe symptom or if you're severe sickle cell patients, then you'll be more sensitive to pain. So basically there is this stimulus and the response set up here on the right. And as a pain, we give a hot heat. So this is like a small iron, and it heats up very rapidly with very precise temperature control and timing control. During that, we look for the microvasculature vasoconstriction response that can be seen on the finger. For that purpose, we use laser Doppler flowmetry and photoplethysmograph or pulse ox. And you can see this is a global vasoconstriction response because it's not on the same side. So let's quickly first look at the signal. You'll see that as we give the heat pain, you can see the microvasculature vasoconstriction response. However, problem is that the vasoconstriction responses can happen randomly. And even worse, when the subject have a big sigh, then that also induces vasoconstriction response. So it's very confounded and difficult to actually objectively quantify how significant the vasoconstriction response to the pain. So here was our solution. Instead of giving one sporadic pulse, we have a train of pulses with a unique randomized pattern of different amplitudes and different interpulse intervals. But this whole train is about 6 or 7 minutes of stimuli. The temperature varies from 32 degrees Celsius to up to 52. And this way we're making sure that we were looking for a specific vasoconstriction pattern that corresponds to this particular pattern, not the randomized once or twice chance of patterns. So finally, let's look at the data. During the heat pulses, you can see the responses here. So on the top, let me try to orient you here, is the heat pulses. These are in degrees Celsius, and you can see this is idle temperature. And there was actually task minimum and max and task randomization. So task randomization was a task that I introduced just before. But before that, we had to determine each individual's minimum and the maximum sensation of the heat. So this is where we determine the minimum and maximum by manually ramping up the temperature, and the subject would say stop when they feel the minimum amount of sensation, and this is where they say stop when they cannot tolerate the heat pain anymore. So these are the two different minimum and maximum point. And based on that limits, the randomized pulse has been configured. And of course, you can see these 5-minute resting period so that they don't overlap, or the response don't overlap. And before the whole task to begin, we have 5-minute quiet baseline when subject just sits down quietly. And then we also have an extended baseline measuring the responses more spontaneous. And during this time, we measure the laser Doppler flowmetry on the right finger, which is the ipsilateral side of the pain, and the contralateral side of the pain. And on the contralateral side, we have a PPG pulse ox. And this is the amplitude of PPG pulse ox, which actually can represent the amount of volume or amount of blood volume in the finger. Therefore, it can reflect the vasoconstriction amount. Now, the first observation is during the baseline, the blood flow on your system is going up and down. But of course, you can see during the pain, it definitely vasoconstricts in terms of the whole baseline, and this fast changes according to these each pain pulses. Same as for the randomized pain. Now we have this beautiful signal. How do we quantify this into numbers? That's next. Now let's talk about cross-correlation and cross-correlation coefficient. So you'll see them a lot in signal processing because it can quantify the strength and direction of the similarity of the two waveforms. And it will be a function of time lagged applied to one of them. So I'll show you what I meant using an example. So in terms of coefficient, cross-correlation coefficient, so to speak, is represented by the letter R in our case, and it will range from -1 to 1. So 0 being no relationship, and -1 being perfectly negative correlation, and 1 being perfectly positive correlation. It means it's identical signal. And basically you can get the correlation coefficient at each time lag using this formula. So you can see that basically it's a covariance between the signal X and signal Y divided by their standard deviations. So basically the R is the normalized version of the covariance, where the covariance can be calculated by this. You can see that for each of the signal, their means are subtracted. So basically you get the deviation from the mean of each signal, multiply them per each sample locations, and sum all of them. And this is divided by the total number of samples. So that's the covariance. So here's the intuition of how we get the correlation or correlation coefficients. Let's start with this formula. But in this case, let's just assume our standard deviations for these X and Y are just 1, negligible, so cross out. And let's say the means are also 0. So they're time series around the 0. So okay, so we can cross that out. And for the example's sake, let's not worry about number of samples. Let's say we have a constant n and it's just given size. So basically to get hypothetical R, we can get that by multiplying the X and Y and sum them all together. So this is the X, which is around, which should be around mean of 0 and the standard deviation of 1. And same as to Y. And over time, when you plot them, it looks like this. So the question is, are they related? First of all, at time lag 0, what we'll do is we'll multiply each of the samples. So this is given here, if you want to look at the details, and then add them all together gives me minus 1.44. We do the same thing as you give a lag to one signal. So this case is lagged by 1, and then the correlation will be minus 0.48, and time lag of 2 means you shifted 2 times. It's now 2.4. I would say high number in a positive direction, and as you slide even more, it becomes negative again, 1.12, and so on. And from this observation, if we wanted to find the best positive correlation, then at time lag 2, we found the most positive one, which is 2.4, and that's this alignment. And you can see that patterns are actually matching that. So it's reasonable to say X and Y trends are aligned at lag unit or time unit 2. And you can do the same thing in MATLAB. So here's a MATLAB code, which you can briefly experiment using xcore function. And in this case, I shifted the x, so I ordered, I had to put in this order, y comma x. And when you plot the correlation in my lag, you will get the same thing as in our table. And of course, this is not the normalized one because I just want to show you the trends, but it was mathematically not rigorous. And in MATLAB, there is another function called core. It can actually give you a normalized correlation coefficients using different types of method. For example, Pearson, Spearman, which is more like a non-parametric method, and so forth. So I recommend you try that function as well. So in reality, if we had computed the correlation coefficients correctly without all the other assumptions, we would have gotten R values from -1 to 1. And usually we would like to use them because it's useful to compare different things as an apple to apple.